Hello, this is a statics problem where we're going to solve for the resultant force through the addition of the component forces of each one of these forces. Okay, we have a problem here that is a bolt A, and this bolt A has four forces acting upon it: F1, F2, F3, and F4. And the problem states here is that we're going to determine the resultant force on that bolt. And you may ask, why are we trying to even attempt to solve for the resultant force? Well, the resultant force will be the equivalent force of the combination of these forces acting on a specific angle with respect to this x-axis. And the reason why we want to know that resultant force is because that force will be used to determine the type of bolt that's going to be used here, and also the connection itself, so it can resist that force. Okay, let's start. So here, determine the resultant force of the bolt. To solve for this, the first thing we want to do is resolve each one of these forces, F1, F2, F3, F4, into their rectangular components. And when I say rectangular components, each one of these forces here, for example, this 80 Newton force at F2 has a individual Y component force and has an individual X component force. And so do all the other forces. Okay, we're going to determine the components of the resultant force by adding each one of these individual component forces in the corresponding x and y directions. So we're going to sum up all of the x's, F1, F2, F3, and F4x, and all of the Fy's, the y components, F1, F2, F3, F4y's. When we sum these up, though, we have to sum them up algebraically. And what that means is that if you have, for instance, F1 will have an F1x force acting along this x-axis pointing to the right. When a component force is pointing to the right towards the positive x direction, we're going to label that with a positive value. If we have an x component force acting towards the left, like we do here in F2, and that's pointing towards a negative axis, we're going to, when we calculate that component force, we're going to provide a negative value to that. And the same goes for the y direction. Any component force, like an F2 or F1, that would be pointing up in its y component would get a positive value. And again, any forces acting down, such as F3 and F4 y component forces, will both be assigned with negative values. Okay. So, and then step 3 will be, once we determine the resultant component forces by summing up each one of these individuals with respect to each other, we will then calculate the magnitude and direction of the resultant force. Okay, here's the solution. So I put a copy up in the top left corner here of the original problem that was stated, and down below I created a force diagram at point A, showing again F1, F2, F3, and F4 forces, as well as in red arrows you will see each one of their individual component forces and their sine or cosines to determine, based on the angle with respect to the axis, to determine the component forces. Okay, so we take F1 and its magnitude was 150 newtons, as it's shown here, and we did, to calculate its x component force, we took the F force and we multiplied it by the cosine of the angle 30 degrees with respect to the x-axis, and that provided our x component force, and that would be a positive value. Like I stated earlier, it's acting towards the right, and there's our positive value right there. Okay, then we come over and we do our y component force. The y component force would be the sine of that same angle, right, pointing up. And since it's pointing up, it would be a positive value, so we took 150 times the sine of 30, and we found the solution to be 75.0, and it would be a positive value. And then we do the same correspondingly for the F2 component forces, which, if you noticed here, F2 in the x component force, right, which is going to be 80 newtons times the sine of 20, is pointing towards the negative direction, negative x-axis, so we gave it a negative, assigned a negative value to it, and calculated 80 times the sine of 20 degrees, and we got 27.4 with its negative value. And again, with the cosine of the angle, 20 degrees makes with respect to the x-axis. We solved for its y component force is 75.2. And then we did the same for F3. F3, it's pointing straight down. Since it's pointing straight down, it has no x component forces, right? It only has a y component force, which is the entire force magnitude. So when we came over to here, we placed 0 in the x component value, and the y component had the entire magnitude of force, 110 newtons, and it's acting down, so we gave it a negative value. And then F4, again, we used trigonometric functions of sine and cosine to solve for the x and y component forces, and again, signed its positive and negative values based on the direction. Great. Okay, so now what we do is we sum up each one of these individual x and y component forces. When we sum them up algebraically, we receive the value in the resultant x component force wound up being a positive 199.1 newtons, and the resultant y component force wound up being a positive 14.3 newtons. The Rx, the resultant x and the resultant y, what it creates is a force triangle, right? We have an Rx and an Ry force here. It's creating and they're orthogonal to each other, right? So they create a right triangle, where the hypotenuse of that right triangle will be our solution for the resultant that we're looking for. So since we have Rx and we have Ry, we can solve using Pythagorean's theorem, right? C squared equals A squared plus B squared to solve for the resultant force. And we can use a simple trigonometric function, sine, cosine, or tangent. You remember the old SOHCAHTOA, right? Sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, or tangent is equal to opposite over adjacent, to solve for this alpha angle. And that alpha angle is the direction at which that resultant force is going to act off of that bolt head. Okay, again, just to reiterate, once we have the resultant and we have the angle, we would use these values again to design the bolt and any potential shearing issues associated with it, or also the connections to the bolt. Okay, so setting up our resultant force triangle, we use Pythagorean's theorem. R squared, right, or the square root of 199.1 squared plus 14.3 newtons squared, and the solution wound up being 199.6 newtons as our resultant force. And then we used tangent. This time you could use sine or cosine at this point because you already have the answer. I generally like using the tangent because we've already solved for these component forces up here, and it eliminates the possibility of an error in Pythagorean's theorem. So tangent is equal to opposite of adjacent, which would be 14.3 newtons over 199.1 newtons, and we take the inverse tangent function of that to solve for alpha, which is the direction of which that resultant force is going to act with respect to the x-axis from that bolt head. And that solution wound up being 4.1 degrees. So there you have it. Okay, that's how you calculate its resultant in its direction by summing up the x and y component forces. Thank you.